Hi there, my name is Joe Izraelevitz. I'm an assistant professor at the University of Colorado Boulder, and I'm here to present Acuerdo, Fast Atomic Broadcast over RDMA. This is joint work between the University of Colorado Boulder and the University of Surrey and Umdea Software Institute. So what is Acuerdo? Acuerdo is a novel algorithm and implementation for fast atomic broadcast on RDMA, which achieves its performance by minimizing weighting. Namely, we intend to minimize weighting by taking advantage of several techniques. First, we're going to leverage RDMA FIFO delivery. We're going to implement an efficient catch-up mechanism for replicas that fall behind. We're going to be able to tolerate transient delays within the network. And finally, we're going to introduce a novel leader election for leader failover. All right, so how do we intend to present this information? So this talk is divided up into basically two parts. The first is understanding the problem of atomic broadcast and the tool of RDMA. And secondly, we'll see how we apply our tool to this problem using our strategy of minimizing weighting in the second part of the talk, namely achieving the goal, our strategy of minimizing weighting, and also how we implement this design decision into our algorithm design. So first, the problem and tool for solving it. Atomic broadcast is a network protocol or a network mechanism used to replicate databases or other fault-tolerant software for reliability. In this example, we have a replicated database replicated across 3 nodes, and we have 3 clients that intend to send messages to update this database. These clients are going to send messages, generally updates, to the database, which again is replicated across 3 copies. One of these copies is going to implement the atomic broadcast mechanism and is going to lead the protocol to ensure that all copies of the database are mutually consistent, that is, they all represent the same information. In order to do this, this leader needs to ensure that all messages from the clients reach all replicas in the same order. So, as part of its job, this leader of the atomic broadcast protocol is going to order all of the incoming client updates into some fixed order, which is sent to all copies of the database. And it's going to ensure that all of these copies reach all of these messages reach all copies of the database. By doing so, we know that all database replicas have the same state, that is, they've applied the same sequence of operations to their local state. And so consequently, we have, in this case, 3 copies of the same database. This allows us to tolerate a failure. If one of these replicas goes down, we know that we have at least 2 more that we can fall back to ensure that we haven't lost data. In general, these protocols avoid data loss on failure, and the protocol works if a majority doesn't fail. As we expect in this case, where we have 3 databases, we can tolerate 1 failure, but we can't tolerate 2. We need to ensure that a majority of our copies stay up. The problem with this configuration really is just that it's slow. We'd like some way of implementing this primitive in a faster way. So in this work, what we intended to do was to leverage some emerging trends in hardware in order to accelerate atomic broadcast. Enter RDMA, Remote Direct Memory Access. This is a new fast protocol where most of the protocol is offloaded to the network card as opposed to being processed within the CPU. In this example, on the left, I have the local node, which will be initiating the RDMA request, and the remote node, which will be receiving it. Important for RDMA, you'll note that the remote CPU is not doing anything. It's just going to be sitting there whistling or whatever, and isn't needed in order to receive these packets. This is important because it bypasses not only the CPU, but also the kernel on the remote node, and allows us to basically have a faster network protocol. All right, so how does this work? Well, first, the local node is going to initiate an RDMA request. It's going to communicate from the CPU to its local NIC in order to say, hey, I want to do an RDMA access. The local NIC then communicates with the remote NIC and indicates that it wants to remotely read or write to the remote memory. That is, from the local to the remote node, we're going to access the remote node's actual memory directly. The remote NIC, upon receiving the request, can then access directly the remote memory and either apply a read and return the result of the read back to the local node, or apply a write and directly modify the memory of the remote node. So RDMA is fast, but the interface is different. We aren't supporting something like a RPC, where the receiving CPU is going to unpack something and do something for the local node and then send back a response. Rather, we're doing direct memory accesses to the remote node. But it's fast. So how can we leverage this for atomic broadcasting? All right, so we've understood the problem of atomic broadcast, and we've understood the tool that we intend to use, that is RDMA, for accelerating this. So now how are we going to take this tool and apply it to the problem, and what strategies are we going to use? Our goal is to minimize waiting. We don't want to wait for any particular replica as we go through the atomic broadcast protocol. Ideally, we can just kind of continue on and not need any sort of response from a remote node. This is the ideal, and we try to get as close as possible. And we use several design strategies for implementing this. So the first is to leverage RDMA FIFO delivery. RDMA is going to deliver messages in FIFO order, first in, first out. And so what this means is that the receiver, when they acknowledge some received message, this implicitly acknowledges all prior messages because we're receiving all of the messages in the same order they were sent. This FIFO delivery mechanism and this implicit acknowledgement allows us to do efficient catch-up. So a database replica that is delayed should ideally catch up quickly. We don't want it to fall further and further behind. By leveraging RDMA FIFO delivery, we can avoid acknowledging every message, and we can just kind of acknowledge the most recent message because it implicitly acknowledges any prior message. We also want our algorithm to tolerate transient delays within the network. Networks can hiccup, they can have packet retransmissions. And so if we have some slow node, which isn't responsive for a small period of time, we don't want to need to wait for them. We'd rather just carry on and expect them to catch up, ideally using our efficient catch-up mechanisms if possible. Finally, in Acuerdo, we introduce a novel leader election protocol, which ensures that on leader failure, we avoid transferring large amounts of states from other replicas back to the leader. What this means is the leader, the new leader, upon taking over, can immediately start broadcasting messages from clients. Acuerdo has 3 modes of operation. This is pretty common for atomic broadcast protocols. The broadcast mode, which is the normal mode of operation in Acuerdo. This is where we're receiving messages from clients at the leader. The leader then orders and broadcasts these messages to the followers, and the followers acknowledge that they have received this message, so the leader knows that the messages have been appropriately replicated. Broadcast ideally carries on as long as possible. If the leader fails, however, we need a backup plan. This is the election mode. So if the leader fails, we need to select a new leader from among the remaining database replicas. All replicas are going to vote in some sort of principled election. And in Acuerdo, we're going to guarantee that the most up-to-date node, that is the node that has received the most messages from before, is going to win. Finally, we have the transition node. Once a leader has won an election, he needs to notify all of the other replicas of his victory and make sure that they're caught up to what the new leader knows. So he's going to broadcast any missing messages that some of his followers may not have yet received. So in the bottom, I will note our broadcast mode is inspired by ZAB. It's very similar to the ZAB protocol. However, it's optimized for RDMA. We use several RDMA techniques for the actual implementation of it. And for more results, you can see the paper, or for more details, you can see the paper. I'll now go into a brief overview of how the Acuerdo protocol works and work through an example. We're going to start our example in the normal broadcast mode, that is, we're receiving messages from the client, accepting or getting them at the leader is going to rebroadcast them to the other nodes within the instance. In this particular example, we're going to assume from the start that node 1 is the leader and nodes 2 and 3 are the followers. Our broadcast is going to begin in leader epoch, round 0, node 1. That is, for this entire time until we go into election, we're going to say all of these messages belong to a particular leader epoch, which is in which node 1 is the leader and we're in round 0. We use this epoch to tag all of our messages. So the leader, node 1, is going to receive messages from the client and rebroadcast them both to itself and to the other nodes 2 and 3. What you see here is node 1 has received 2 messages from the clients, perhaps different clients. It orders them as message 1 and message 2 within epoch 0, 1, as round 0, with leader node 1. These messages are immediately broadcast to all of the nodes. We don't need to wait for any acknowledgement in between these 2 messages. However, at some point, the nodes need to acknowledge that they've received these messages. And indeed, we'll see this in the next step. Node 3 is going to notify its leader that I have received message 2. In acknowledging the acceptance of message 2, node 3 is also implicitly acknowledging the acceptance of message 1, again, because of RDMA FIFO guarantees. The leader, node 1, receives this acknowledgement, this acceptance message, and now knows that message 1 and message 2 of epoch 0, 1 have been received and acknowledged at least 2 nodes, namely itself and node 3. At this point, the message has been replicated across a majority of the nodes in the instance. Again, we require 2 nodes in order to reach a majority of the 3 nodes that are in the instance. And so consequently, this message can be committed and delivered to the local database at node 1. And so what's shown in green, message 1 and message 2 of epoch 0, 1 is delivered to the local database at the leader. He also notifies his followers, nodes 2 and 3, that it is safe to commit these messages to their local copies of the database. He sends the commit message for message 2 in epoch 0, 1. Upon receiving this message, nodes 2 and 3 can commit this message and apply them to their local state. This is kind of the normal case. As we approach the end of the broadcast, we're going to see an abnormal case. Node 1 has received a 3rd message from the clients and begins to broadcast it both to itself and to node 3. However, before it manages to send this message to node 2, it fails and times out. Nothing else happens on node 1. Nodes 2 and 3, having not heard anything from their leader, node 1, for a little while, are going to transition into an election because their leader has failed. Node 2 is the first to enter election and is going to initiate the election via a vote. That is, he's going to try to vote for the most qualified leader amongst the remaining replicas. His vote takes the form of a proposed epoch and the most recent message that he is aware of. That is, he's going to vote that the new epoch will be round 0, node 2, where node 2 himself is the leader, and the most recent message that he is aware of from the previous epoch is message 2 of epoch 0, 1. Again, the previous leader failed to send this last message to node 2. Node 3 also enters the election. He proposes himself and says that the new epoch should be 0, 3, that is round 0, with himself, node 3, as the leader. He also notes that he has received 3 messages from the previous epoch, so the most recent message he has received is message 3 of epoch 0, 1. Node 2 receives this message and says, I am not the most up-to-date follower. Rather, node 3 has more information than I do. So node 2 is going to change his vote and vote instead for himself, but rather for node 3, who is, as far as he is aware, the most up-to-date node in the instance. He changes his vote to epoch 0, 3, with 3 being the leader, and with the associated tag of message 3 from the previous epoch 0. At this point, node 3 has received 2 votes for himself, namely the vote from himself and node 2. He has won a majority of the votes in the election, and at this point, he knows that he is the most up-to-date node within all voting nodes, and can take charge of the instance. He has won the election. The final stage in the Acuerdo protocol is to transition from our election protocol back into normal broadcast. That is, node 3 needs to secure his victory. In order to secure his victory, or to notify his followers of his victory in the election, node 3 is going to send a special message called a diff to all other nodes in the instance. This diff serves 2 purposes. First, it contains all messages that the other nodes might not be aware of at the end of the previous epoch. In particular, this diff will certainly include the message 3 from epoch 01, that is the message that failed partially at the end of the previous epoch. The diff also serves to notify all followers that node 3 has won the election and is now the new leader. Having sent the diff, this is sufficient to notify all followers that node 3 is taking charge of the instance, and so he can immediately start processing client commands. Nodes 1 and 2, upon receiving the diff, can accept that node 3 has become the leader, and nothing else needs to happen. The leader can immediately start receiving client messages and broadcasting them. He doesn't need to receive any sort of acknowledgement from nodes 1 and 2 before processing and forwarding and ordering incoming client messages. So the first message that he receives from the client will be message 1 of the epoch 03. Acuerdo minimizes waiting at several points within the algorithm. Let me show you how our principles apply to this overall protocol. First, we're leveraging FIFO delivery. When you receive several messages in a batch, you only need to acknowledge the last one, because FIFO delivery implicitly implies that the prior messages were already received. So in this case, node 3 is accepting message 2, implicitly acknowledging message 1. Secondly, we can tolerate transient delays. Because we're a quorum system where we only require a message to be accepted at a majority of nodes, if a node is slow for a little bit, that's fine. We're just going to leave him out of the quorum and expect that in the future, he'll become part of the quorum, which indeed is what happens with node 2 in this instance. Next, we have efficient catch-up. So node 1 has received the acknowledgement for his first 2 messages and has sent out the commit to nodes 2 and 3. Node 2, you'll note, has not sent any messages at all. So if he was descheduled for long enough that he didn't need to send a message and he receives this commit from the leader, he can immediately commit messages 1 and 2 and doesn't need to do anything else. This means that message nodes that are behind the bleeding edge of the protocol are going to be more efficient because they send fewer messages and ideally are able to catch up to the rest of the instance. Finally, our principled leader election ensures that our most up-to-date replica is elected. What this means is as soon as node 3 wins the election, he can immediately send the diff and start processing client messages. He doesn't need to wait for any additional acknowledgement from nodes 2 and 3 before doing this. He can immediately take charge. Acuerdo has good performance. I'm going to call out a couple of results from the end of our paper. There are more detailed results, obviously there. I want to talk about both configuration in which we have a small message size and a small cluster, and a large message size and a large cluster. When we have a small message size of 10 bytes and a small cluster of 3 replicas, Acuerdo has the best latency and strong throughput across all of the systems that we tried. Most of these are, or at least a majority of them, are RDMA. For large message sizes and clusters, the message size is 1K, and the number of nodes is 7. Acuerdo has the best latency and also has the best throughput of leader-based solutions. You'll notice there's this extremely dominant dark blue line over on the right-hand side, which has significantly higher throughput than Acuerdo. This system is a leaderless virtual synchrony configuration or protocol. In virtual synchrony, we can avoid electing a single leader, and so consequently we can use the throughput of all replicas within the system. The cost, however, is that if any node fails, we have a relatively long failover. And so it can't easily tolerate small network hiccups because we're expecting all nodes to be operating at basically the same speed. So to conclude, Acuerdo is a novel algorithm and implementation for fast atomic broadcast on RDMA, and it achieves its performance by minimizing weighting. Our strategies include leveraging RDMA FIFO delivery, efficient catch-up in the case where we fall behind, tolerating transient network delays in order to avoid hiccups from derailing our performance, and finally, a novel leader election protocol that ensures the most up-to-date leader is elected in the event of leader failure. Thank you very much for listening, and I hope to see you at the session. Take care.